Hello, I'm Tomas Ostasevicius. I'm actually from the same group as Rowan, and I'll be talking very quickly covering the HyperSpy and SamFire and how we use those two tools for big data analysis. And as Rowan, I hope, gave you the impression that in electron microscopy we have data sets that have a lot of dimensions and they're very quickly becoming very big. So whenever you add additional signal or just want to have more resolution, it quickly goes from tens to hundreds of gigabytes. So our problem that we have faced is that simply the data set doesn't fit all at once in the computer memory, so we have to get around this. And there are multiple things we want to do with the data. Obviously, we want to be able to visualize it, all 6, 7 dimensions, probably not all of them at the same time, obviously, but we still want to have a look at it. We want to do some pre-processing. We don't want to have to write all the algorithms ourselves. We want to be able to use image analyzing techniques that already have been implemented in libraries, as well as one-dimensional algorithms that work on one-dimensional data, but all for these 7, 8 dimensions, whatever we have. And finally, we want to do the actual analysis of the data sets, which in our case involves machine learning and nonlinear fitting in general. And we looked for a package that enables us to do all of these things conveniently and quickly, but we couldn't find one, so we came up with our own. We call it HyperSpy. It's completely open source. It's written in Python, actively developed, probably too active from my point of view. I spend way too much time doing that, but you're very welcome to have a look, try it on your data set. We may not have the features that you will need exactly, but we are very quick actually implementing those, so just let us know what to do. Finally, I will talk about the nonlinear fitting and the problem, or rather the solution, how we solve that in the highly dimensional data sets. So the traditional fitting approach, let's say you have a spectral image, and which is the pointer, there you go, and in each of the pixels you have a spectrum. In this case, spectrum, it could be another image. So essentially you have a multidimensional data set. And since it's a nonlinear fitting problem, you have to start very close to the real solution, otherwise the algorithm gets lost and you get lost in the parameter space. I'm sure it's a problem that many of you have faced, and it's a very common thing. But traditionally what you do is you start with a proper solution and you go pixel by pixel, start copying the previous starting values to the next pixel, and the problem, of course, when one of the pixels fails and you just propagate the bad solution. It's actually been done only due to historic reasons, because previously people only have like 9, 10, well, 200 pixels at most. So it's not a big problem to actually go manually and check all of those that failed, and you can fix it, and it's fine when you have not a lot of data. But now it becomes a real big problem for us. So what we did instead, we came up with SamFire, which stands for Smart Adaptive Multidimensional Fitting. It's a very long name. So what we do instead, we use data to determine which pixel next. We don't just go in the order that they were stored in memory, in the computer memory. We also use all available information. We don't just copy the previous value that we had to the next pixel. And finally, we actually check if the fit succeeded in every single pixel. You have to have some metrics, like reduced chi-square, for example, for that. But once you have it, you can prevent bad pixels that do not fit or were just outliers from contaminating, so to say, your fit results. So how SamFire would tackle a similar data set that's slightly bigger. I will not show the spectral dimension in this case, but here still black pixels will be the non-fitted ones. The blue pixels will correspond to already fitted pixels, and there will be a gray value around each fitted pixel that will essentially add up around all the fitted pixels, and so we just select the brightest one as the next one when picking which pixel to fit next. So that's how it looks like. And the arrows also show how we get or rather where we get the starting values from. So it's not just one pixel, the last value that we used to solve the problem. Instead, we use a local average that's weighted depending on your problem. As you can see, there's one pixel, this one, that just failed to fit, and it's fine. I mean, it reduces to the not fitted state, so to say. and it doesn't propagate, and it's not a problem for us at all. Finally, it works. I've actually done this to a number of data sets, and it actually works. Yes, we've done stuff that this essentially wasn't possible to do before due to the starting value problems. It was just too sensitive to the starting value, so you have to start very close. All the pixels are somewhat similar, but it's just not viable to do by hand because there's just so much data. I want to thank you for the attention as we look how SamFire tackles, the actual SamFire tackles the spiral data set. I want to thank the funding bodies, Francisco Della Pena, who's actually sitting here, Paul Mishli, and Raul Arenal for giving the beautiful data set that I had to work with. Any questions?
So is this hyperspectral image analysis tool, is this something that you developed or a whole group developed?
The HyperSpy is developed for open source, obviously. Francisco probably spent the most time doing that, and he's like, it's like his third child, I would say. I worked on the SamFire myself mostly, with a lot of help from Francisco with the ideas.
I mean, open source, is it also some kind of GitHub thing that
yes.
people can make changes and see what they...
HyperSpy is on GitHub and open source. Yeah. SamFire is not yet published, but we really hope to do that in the next month or two, and it will be available as an open source as well.
Okay, that's great.
Thank you.
Okay, let's thank Thomas again.